So yesterday we talked about alcohols, and that's where we introduced an oxygen atom into our hydrocarbon system, all right? So we had a hydrocarbon, all hydrogens and carbons, and then we took one of the H. There's many ways of thinking about what an alcohol is, all right? You can imagine that we, for an alcohol, took an H off, put an O in its place, and then attached the H to the end of that, all right? Or you can imagine it as inserting the O in between the C and the H. However you want to think of it, it doesn't make any difference. The key is that in the end, we've got this now OH group that's kind of standing out in the structure. Again, reactive-wise, this is going to have a dipole, right? There's going to be a large delta En here, and so there's going to be a slightly negative charge on that O with a slightly positive charge on that H. The rest of it is nonpolar, so reactions tend to happen around that region. And that's why we call it a functional group, because reactions tend to happen around that thing. Okay, so we talked about how to name this. This would be 1-butanol, all right? We talked about the different classifications of alcohols. This would be a primary alcohol for many reasons. One, the key carbon is only bonded to one other carbon. The other reason that I learned, the OH is at the very end of a chain, all right? And you'll notice, again, the key carbon has two H's, all right? So that makes it primary. If my alcohol was in the middle of the chain, my OH was there, that would be secondary, key carbon connected to 2. And if we had a branch and the OH was connected to that, that would be a tertiary or third-degree alcohol, 3 carbons connected to the key carbon, no H's on it, all right? And we named them, and we talked a little bit about their properties. They tend to have higher melting points and boiling points because they can undergo H bonding. So now we want to talk about a related group to it called the ethers. And ethers, again, they're very much related to alcohols. And that's because we have a single oxygen, except instead of it being placed in between a hydrogen and a carbon, we break the chain and we stick the oxygen in between 2 carbons. So it's as if we've put the oxygen, instead of at the end on an H, we've put it right into the chain. We've built it right into that main chain. And that's what makes an ether. It's got the oxygen that are flanked by 2 carbon groups, 2 alkyl groups. All right? So alcohol has oxygen singly bonded. Ether has oxygen singly bonded. Alcohol has oxygen singly bonded to a hydrogen, but the ether has the oxygen singly bonded to 2 carbons. Okay? It's a polar molecule, but it doesn't involve hydrogen bonding because I don't have the oxygen directly bonded to the hydrogen. There is a dipole difference here. Again, we will have a delta negative with some delta positives on the carbons because it's going to draw the electrons that way. But it's not as strong as the H bonding situation, so this simply undergoes dipole-dipole interaction, all right? So its melting point won't be quite as great as the alcohol, but it'll be a little greater than just the alkane, which is totally nonpolar. Okay? Now this next slide, you've already started to write down, so you don't need to write this down. Actually, what you can do is you can write this bullet here, because this bullet right here is specific to the ether. But we already wrote this on that page that I told you to write on your own, which was called Properties of Organic Substances, I think is what I wrote, right? But the top bullet is a good one to write. Ethers have higher melting points than the hydrocarbons, but lower melting points than relative alcohols, okay? And when we say relative, we mean they would have the same carbons and hydrogens. So if I took my example here, got rid of all these extra things that I put on it earlier on, and I just have butane, right, then butane would be the lowest melting point, boiling point, be very volatile. That would be a little higher, and then that would have the highest melting point, boiling point. All right? So again, no need to draw this bottom part. That's on that page that I told you to write down yesterday, separate page that we will be making reference to that I call, just properties of organic substances. Lowest melting point, boiling point, medium, and highest. All right? Actually, when we're done with all of our compounds, we're going to find we can actually put titles to all of these for the different intermolecular forces. Only London forces govern this. London forces and dipole-dipole govern this. London forces and H bonding govern these. And so we can put them in the groupings depending on what their intermolecular forces are. Okay. Well, naming ethers. You've got a page for this. This is already the page that I gave yesterday. So I'm going to just switch over to my Word document. And I actually have the aldehydes one. Let me open the other one. So I need again to find for naming alcohols and ethers. We've already done the alcohols. Now, this naming method is a little goofy. It's a little strange compared to what we've done up to this point. Up to this point, we've had a definite functional group, and it ends in whatever the ending describes that functional group, ene, ine, all. But for ethers, it's kind of an odd thing. It's kind of strange in which we name it. We don't have a special naming system. We still have the parent chain, but the parent chain is going back to the alkane. All right? Let me go through it. I'll show you an example, and then hopefully the light will go on. So it's like we're going back to alkanes. The second thing is we treat the second alkyl group, the shorter one, and we give it the oxygen, and we give it a name called an alkoxy group. What a great name. All right? So we call it an alkoxy group. It's an alkyl group, carbon, hydrogen, et cetera, with an oxygen, and so it gets the name alkoxy. And I'll show you what I mean in a moment. We replace the YL ending with oxy, and I'll tell you in a moment. Give it a position number on the parent chain. Now, this alkoxy group will have the lowest position because it's the functional group. Name the branches that before, place all the branches in alphabetical order. Okay, let's take a look at this one here. Actually, let's zoom in. All right, move down, zoom in. Let's do a good old clear here. Clear ink. And I'm zoomed in on the wrong one. Moving down, right there. Okay. We don't want that shapes thing up. Let's take a look at this one. So here we have an ether. All right? It's got an O in the middle. We want to name this thing. We need to break it into two chunks. We need to break it into the parent and then the shorter one with the oxygen. So here I've got 2 and here I've got 1. So the parent is right here. It's 1, whoops, getting my pen. It's 1, 2. And the group is this one right here. Okay? So the shorter chain gets the oxygen and is named as a branch. And this is not a methyl, but it's a methyl with an oxygen, which makes it methoxy. Is that fun? That's a fun name. That makes it a methoxy group. All right? So now we go back to naming our alkanes. We could even have a double bond in there if we wanted. We would just treat that shorter chain with the oxygen as a special branch that has the name methoxy or ethoxy or propoxy. All right? So 1, 2 is ethane, like we started way back at the beginning of this. ethane, all right? And in the number 1 position, I have methoxy. Now, if I put it in the number 2 position, that's really the same thing, right? So that's one of those cases where I don't need the number because it's really going to get me the same thing. So this is methoxyethane, all right? So let's take a look at this one. Now, they're the same, 3 and 3. So it doesn't matter which one we pick. I'll pick this as the chain, 1, 2, 3. And this then becomes my big giant branch. The base name, propane. And this is a propoxy. Now, this propoxy group could go here, which is what it is, or it could actually come off of this one. That would make it different. So I do need a number. What carbon is it on? It's a 1-propoxy. 1-propoxy, whoops, too much space, propoxy propane. Yes? Because I could take this thing, and I'll just take a different color. I could have it coming off of here, O, C, 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 right? And if I did, and I ignored this thing, then I'd have the propoxy group hanging off of the number 2 carbon, and it would make it 2-propoxy propane. You see what I mean? It would be a different molecule. All right? I'll get rid of this guy here. Doesn't matter. I got to get rid of the whole thing anyway. Okay? So let's move over and do the last one. Oops, moving over. So I've got a short little branch with an O on it, and then I got this big long chain, right? So that's my branch right there. That's my branch right there. And I have another branch over here. So now I've got a little more complicated. You might think that that's a branch there, but that actually contributes to the long chain, right? So I've got a chain here of 4. And it's on the 2 because it gets the smallest number because it's the functional group. So this is 1, this is 2, this is 3, this is 4. So my main name is what is the N name of this thing? It's a all single bonds, butane. And now I need my branches. This is what do we call this branch? Methoxy. It's a methoxy branch. And what about this one? Chloro. What comes first? Chloro. Chloro is going to go first in the name because of alphabetical. So 3, chloro, 2, methoxy, and then that rolls right into the butane. All right? So it's a little different in that we kind of go back to our ane, ene, ine name, and we put that methoxy group or ethoxy group, in general it's called alkoxy for any alkyl group on that thing. Where with our alcohols, we had all at the end and we defined that thing with the all and giving it a number. A little different. Okay, so let us do a draw and then we can move on. So let's move back over here. So again, drawing is, I always think the easiest. I work my way backwards. So right there, I'm starting with a hexane, right? So 1, 2, 3, 4, 5, 6. And I've got a 3-bromo. Oops, that's in the number 2 position. Counting errors. Let me use my fingers. 1, 2, 3. There we go. Br. And what's that? Doing things like that? You mean just putting it on the wrong one or things like that? Yeah, yeah. You get rolling and counting and getting too quickly. All right. 4,4-dimethyl. CH3. CH3, right? And a 2-propoxy. Oh, goodness, I'm going to run out of room. O. And what you can do here is you can put a regular propyl group. So C3H7, right? Because it's normally 8, take 1 away. So you can put an O and then just C3H7, and then load with H's. H3, H, that goes around the corner there, so there's nothing bonded there. H, full, H2, H3. Okay? So we've got these alkoxy groups that we use just as branches. Okay? All right. So that is, I'm going to clear this screen before I move on. So we talked about naming ethers, and let's talk a little bit about isomers. Essentially, because between an alcohol and an ether, we're simply changing the position of the O, then alcohols and ethers are structural isomers of each other. So again, here we have ethanol. The O is at the end here, between the H. Put that O in the chain, and we have, what is this? Methoxymethane. We're going to be doing those next, so I already handed that sheet out. So that's for when we get to those. Yep.
Are you going to make a summary page for this?
I think we will. We'll work together on a little summary. We could start that any time, actually. I was just going to get ready to mention that. Usually I give that summary out at the end, but I might even give it out tomorrow, and then we can start adding it to our summary as we go. Because we're starting to gain in number of reactions and number of things, and we'll do that. I'll find that for tomorrow. What's that? Yeah, I can do it here, but I also will give out a sheet at the end of the unit, always do your own summary. But we could work through it all as we move along. It wouldn't hurt. Because we're starting to get more and more reactions, right? And so we need to kind of start getting things kind of in order. And so we'll do that with tomorrow. I'll get it for tomorrow. One little question in terms of naming and isomers. That's again a little homework problem. And I'm hoping this is becoming boringly repetitive, but now we'll talk about reactions of ethers. And that's what we do in organic chemistry. I'm teaching you the functional group, then we talk about their properties, we learn how to name it, we learn some basic reactions. So preparing ethers. That's the summary that I'll give you tomorrow, so you can start. Yep. Ethers are prepared by putting two alcohol molecules together. In the process, a water molecule is eliminated, and the other two parts of the alcohols stick together and form an ether. We've already seen examples of this where we've pulled some water out of a molecule, and we're going to do the same in this case. But this reaction is a little different than the other reactions that we've seen where we've removed water. In this reaction, we are sticking together two larger molecules to make an even bigger molecule. When you put together two larger molecules and kind of weld them together, you can imagine like we're welding things together, building something, we call it a condensation reaction. Now, sometimes students get confused with the term condensation because when you hear the word condensation as new chemistry students, you automatically think of water condensing and forming a liquid, like when you have fog on your mirror in the morning after you take a shower. It condenses and it sticks. That's not what we mean by a condensation reaction, all right? I will explain in a moment why we use this term condensation. No, because you'll make a mistake. You will make a mistake. You are taking water out of it, but you take water out of other reactions as well. They're not condensation reactions. And so then when I ask you to tell me what type of reaction it is, you make a mistake because you think of the water being taken out as opposed to the two molecules coming together to make a bigger molecule. Because that's what makes a condensation reaction. And that's why I'm being very deliberate about this discussion. I'll give you a contrast to what isn't a condensation reaction, but we still take water out of it, right? And I'll tell you why that isn't a condensation reaction. The key to the condensation reaction is two molecules combine to form a larger product. There it is right there. Two molecules combine to form a larger product with the elimination of a smaller molecule, but notice it says such as water. It doesn't have to be water when you do a condensation reaction. So let me show you an example of a condensation reaction, and then I'll contrast it with something that isn't a condensation reaction that we've already seen. So here we've got an example where I have this smaller alcohol reacting with this larger alcohol. And actually, I am going to want to name these. So as you're writing, if you could think about what their name is, I'll take that information from you momentarily. Yeah, excellent. Methanol. Methanol and ethanol. Excellent. Ethanol. And here's what happens. Now, it doesn't matter which molecule I remove the OH and which molecule I remove the H. We have to take an H and an OH off of, both of them, and it doesn't matter which one you take the O off of. Now, I'm sure that chemists have done all kinds of investigating to learn which O actually comes off. I don't personally know that information, and I'm not that concerned about it here, really. If you go on and you work on this in great detail, you'll learn which O comes off. So I'm going to just have this H being removed with this OH for no reason. Doesn't matter. Again, I've already mentioned to you, if you want to suck water off of something, what do we use as a catalyst? Yeah, we use concentrated H2SO4. It is a water-loving thing, and it will take water off of something. So what does that do? That frees up an electron here. It frees up an electron here. They form the bond, so we end up with CH3 with the O, and then that bonded to the CH2, and then CH3. And we have our water left, because we still have to have a balanced chemical equation here. No, that's a good question. I'm surprised someone else haven't asked it when we were dealing with things like chlorine and fluorine. These are not Lewis diagrams. Lewis diagrams need all electrons and all pairs like we did in the last section. These are called structural diagrams, and we use it more prevalent in organic chemistry, and we're really worried just about the atoms and their connections. We're not worried about the existence of the lone pairs. We should know from experience that there are 2 lone pairs on those oxygens, but we don't want to be drawing all these electrons. We're worried about the connections. So these are structural diagrams. They're not Lewis diagrams. We don't need the lone pairs. Okay, let's name the stuff that we get here. What is then the name of our ether that we have formed? So again, longest chain, there it is there. And there's my short group with the O. What's this going to be called? Yeah, methoxyethane. No one needed because either one is the same thing, right? So methoxyethane. Excellent. Okay? So 2 bigger molecules come together to become 1 even larger molecule. Let me contrast that with something like this. CH2, CH3, OH, all right? And we have 1 molecule all on its own. You put it in that good old concentrated H2SO4. You don't have to write this down. If you are, it's not a big deal. But that's also going to rip off of water, right? It's going to take the OH there and one of the H's there. It's going to turn it into a double bond, CH2, double bond CH2, right? And it's going to give us water, okay? We looked at this yesterday. It's a reaction of an alcohol. This is an elimination reaction. We've taken out a little piece from a bigger molecule. We haven't put together 2 bigger molecules. So this guy up here is a condensation reaction, and this is an elimination reaction, and we can say that this is a dehydration reaction because we've dehydrated the molecule. We don't call the condensation one a dehydration reaction, even though we've removed water. The purpose of the removal of water was to weld together the 2 larger molecules to make an even bigger one. So condensation is 2 coming together to become 1, and sometimes a chunk has to come out of it. Okay? All right? Why would we call it condensation? And that's a good question. I'm not 100% sure. But if you make a hydrocarbon into a bigger hydrocarbon, if you make 2 smaller molecules that might be gases, and you weld them together and make a bigger molecule, right away you've increased the London forces because it's bigger, and it may become a liquid. So it might, the molecule itself might condense. Nothing to do with water, okay? It just happens in this case that we have water as our other product, and then that's confusing for new students because you see condensation and you think water condensing on your mirror, or you know what I mean, that type of thing. But it doesn't have anything to do with the water. It's 2 bigger ones becoming an even bigger one. Excellent. So there are some homework questions that deal with ethers, but as you know, I'm going to continue on with the next functional group because that's really what this is all about. The next 2 functional groups are called aldehydes and ketones, all right? And then I'm going to do another pair of functional groups called carboxylic acids and esters. I'm going to stop at that point, and then we're going to have our unit test. So we're going to do 4 more functional groups, 2 and then 2. All right. I hope to get that done by Friday, but I might not. Whenever I get done, the next day will be a review, and then we will have our test. Okay. I am going to, though, have one more naming quiz on Friday, okay? And what's on that naming quiz will be dependent on how far I get today and tomorrow. It won't have the last 2 functional groups. It probably will be alcohols and ethers with aldehydes and ketones. Wherever I'm at, though, I'm going to make a quiz for Friday because I want, again, to force you to think about that naming. It makes you do it, right? It makes you practice it, that type of thing. So there will be a quiz on Friday. Okay. So now I have to switch to aldehydes. Whoops, not that one. I have way too many things open. Here we go, aldehydes and ketones. And it's doing all kinds of fun stuff here for me. There we go. So again, like I said, we're essentially kind of manipulating our base hydrocarbon by adding oxygen, and we're kind of just moving it around, doing various things with it. Alcohols have our oxygen singly bonded to a hydrogen and a carbon. Ethers, we move that oxygen into the chain, singly bonded to 2 carbons. And the next situation we can have with oxygen is we can have oxygen doubly bonded to a carbon. So now we're going to increase the contact of the carbons with oxygen. All right? We're going to actually now take a single carbon and doubly bond it to an oxygen. So we're just kind of progressing with the way oxygen connects with the carbons in the hydrocarbon chain. When we have an oxygen doubly bonded to a carbon, we call it a carbonyl group. Now, for those who have taken biology and who were kind of directed to memorize functional groups, because that's what they essentially do in biology. They say, here's all the functional groups, memorize them and spot them, which is great. There's nothing wrong with that. The way we do it in chemistry, I'm kind of giving you the evolution of where those functional groups come from and how to maybe think about them in a little more of a chemical way. We call the carbon doubly bonded to an oxygen a carbonyl group. I think the biology people, you guys look at that one, right? You look at carbonyl groups, right? Let me show you the way we can create a carbonyl group. Actually, aldehydes and ketones are very much related to alcohols and ethers. If I take an alcohol and I get rid of an H on the key carbon, just like that, and I get rid of an H on the alcohol, like that, all right? In other words, I get rid of 2 H's, then I'm now able to form a double bond with that oxygen. If I do it with an alcohol that is at the end of the chain, then you'll notice that I end up with this carbonyl group that's connected to 1 carbon and 1 hydrogen. That's an aldehyde. When our carbonyl group ends up at the end of a chain, right at the end, on the very last carbon, we have this carbonyl group and then an H, then we have an aldehyde. I could do a similar maneuver with our ether. I could take a hydrogen away from here and a hydrogen away from here, and I can kind of connect these two like this and shift that O up there. So I've kind of put that carbonyl group in the chain. And when the carbonyl group's in the middle of the chain, it's a ketone. Okay? So alcohols and aldehydes are kind of related in the position of where that thing is. And then also ketones and ethers. And I trip over these words all the time. But anyway, okay. So notice that our oxygen is not connected to any H's directly, which means hydrogen bonding is not an option. It is a polar scenario because the oxygen will pull on the electrons from the carbon. Oxygen is very electronegative. So we've got London forces and dipole-dipole, just like the ethers. And therefore, and again, you don't need to rewrite. You're now going back to your page, and you're now just adding. You're going back to your page, properties of organic substances, right? Did I have you make that page? And now all you're going to add is here in that ether group, aldehydes. All right? Because, again, like I said, we could actually do that even at this point. We could put here, these are just our London guys. That's just London. They'll have the lowest. This is our London and dipole-dipole, dip-dip. This one here is London and H bonding. And I said there was two more. There's actually only one more that we'll be looking at to the right. There's one more group to the right, and we'll get to it later on. Yeah, there's going to be one more over here. Yeah, there's going to be one more grouping. When we get to carboxylic acids, there's dipole parts of it, there's H bonding parts of it, and there's London force parts of it. In other words, there's all three of them existing in the same molecule. Makes it really sticky. Okay? So that's just adding aldehydes to our list. Naming aldehydes, let's go to that sheet that I just gave you. Aldehydes are easy to name. Because they're like related to alcohols, right? And that double bond C, that carbonyl group, is always going to be in the chain. We don't need anything fancy like we had with the ethers, like some methoxy or something crazy like that. So the carbonyl group has to be in the chain. And actually, because it's on the end, it always starts the chain. And instead of all, we give it al is the ending. So instead of pentanol, you could have pentanal. All right? Now, in an aldehyde, the carbonyl group is always number one because it's always at the end of the chain. And so we don't need a number to tell us where the aldehyde group is. Remember, the alcohols could be anywhere on the chain. We could put that OH anywhere. We could have a 2-pentanol or a 3-pentanol or a 1-pentanol. But for aldehydes, it's always 1. No need to number the location of it. 2, 3, 4, doesn't matter which way we go, 5. So the base name here is pentanal. It's pentanal. Okay? I do have a group. It's in the number 4 position. It could be in the 3 or the 2 position, so I do need a number. So this is a 4-methyl. Oops, what am I doing, methyl? I'm losing my mind. 4-methyl. Here we go. Let's get rid of that. 4-methyl pentanal. All right? So again, aldehydes are easy. There's that guy there. That's number 1, no matter what. Number 2, number 3, number 4. Here we're being mean again. Look at here. I could have 5 or 6, or I could have, there's a C3, right? I could have 5, 6, 7. That's the longest there. There's us trying to just be mean. Our textbook likes to try to be mean. I don't think it means to be mean, but it does like to put those groups on the end. It just likes to be mean. I will not, on quizzes and on tests and on exams, I put like one mean one out of a big group of them. I'm not out to be mean on every single one. So what do we have here? What is this main chain called? Hept for 7, heptanal, heptanal, heptanal. And I got a branch off of the 2, and I got a branch off of the 4, and I got another branch off of the 4. So now we need some alphabetical. What's going to come first in that branch? C does come before E. I was going to put the ethyl first, but C does come before E. 4-chloro. 4-chloro. 4-ethyl. 2. All right, now I'm in trouble. Methyl. And then that connects over to here, obviously, right? That's how that works. Just like that. That's beautiful. Maybe not. 4-chloro, 4-ethyl, 2-methyl heptanal. That's just fun. That's just fun words, like silly speak. Okay, let's. I'm not even going to move down here. 3-methyl pentanal. Oh, look at, I have pentanal up here, and I've got 4-methyl pentanal, and I'm telling you to draw 3-methyl pentanal. Isn't that a little silly? It's really the same thing, except I'm moving that thing over to the number 3 position. Silliness. 1, 2, 3, 4, 5. Now, as soon as you see the al ending, you're putting double bond O, right? That's what you're doing. That's the carbonyl group. As soon as you've got the al ending, double bond O right at the front, okay? Then you're going to go 1, 2, 3, put your CH3, and then again load with H's, right? Because it's on the end, you can put the H on the outside here. That's typically the way it is. If you were to put the H on the inside, like the way we fill in our H's, I'd say correct. Not a big deal. It doesn't matter where the H goes there. H2, H, H2, H3. Okay? So the al tells you the double bond C is on the end. I could have made that a little larger. I don't know why I didn't. So that's an aldehyde. We've just increased the connection of that hydrocarbon with the oxygen. Okay? All right, let's go back to where we started, right there. We've done the naming of the aldehydes. Excellent. Now, you might think that we might talk next about reactions of aldehydes. But in this case, we go straight into ketones, and that's because aldehydes and ketones are prepared the same way. We prepare them with the same reaction. It depends on the type of alcohol we use to prepare them. That's what determines whether we get an aldehyde or a ketone. All right? So we're going to roll into ketones here. We'll talk about how to name them. And then we'll talk about how we prepare both aldehydes and ketones together because they're prepared from the same stuff. They're just little differences that we need to be aware of in order to determine it. So a carbonyl group, our ketone has a carbonyl group, non-terminal. When we say terminal, we mean the end of the chain, right? So if we have a terminal alcohol, it's at the very end of the chain. If we have a terminal carbonyl group, it's at the very end of the chain, and it is an aldehyde. If we have a non-terminal carbonyl group, we say that it's in the chain, all right, in the middle of the chain. I don't know if anybody wants to add that. I'll add that right there. Non-terminal means in the middle of the chain, of the carbon chain, which means it's flanked by two carbons. It's also polar, and again, it does not have a hydrogen bonded directly to the oxygen, and therefore, it's still just dipole-dipole. So its forces are very similar to the aldehydes. Their melting points and boiling points are actually very similar. And I'm pretty sure our next slide is going to put then the ketones on our good old summary sheet in the same grouping as the aldehydes and what else was in there? Ethers, I believe, right? You got that? Yep. Okay. So again, no need to rewrite here. I'm just adding now to our summary sheet. That's why I didn't want you to have to rewrite it. When I started teaching this course after I hadn't taught it for a while, I used some of the other teachers' notes, and I noticed everybody's writing the same thing over and over again. I'm like, that's silly. Make a summary sheet. So now we've got aldehydes, ethers, and ketones in the same grouping. So if we had comparable ones, meaning they've got the same number of carbons approximately, then they'll have very similar melting points and boiling points. All right. So now we've got our ketones and aldehydes in the same grouping here. Okay, I think we've got that. Naming ketones. Well, I'll switch to the other one, but you're looking at your page, but I'll look at this here. That's where my eyes go to. It ends in "-one", right? So an aldehyde ends in "al", which is at the front, which is kind of weird. But the ketones end in "-one". Okay? They end in "-one". Again, the parent chain has to contain the carbonyl group. So you look for where that double bond is. Now, in this case, that double bond can be in different positions in the chain. So we do need a number this time. For aldehydes, no number needed, always in the number 1 position. For ketones, we do need, all right? If you accidentally think of an aldehyde as a ketone and you give it a 1-one, then you've got a mistake. A 1-one is an aldehyde because it's never in the 1 position. And then name your branches, et cetera, et cetera. Okay. We'll head back to this. We'll clear the screen. Move down here. We'll zoom in a little bit. Okay. Let's take a look at this one. So again, we are locating longest chain. 1, 2, 3, 4, 5. Right? 1, 2, 3, 4. Not long enough. Has to have the double bond. 1, 2, 3, 4, 5. So what's our base name for this before we put any branches? Yep. Yeah, very good. It's a 2-pentanone. 2-pentanone. And now I've got a branch, obviously. That branch could be in different positions, so I need a number. What's our branch? It's a 3-methyl. 3-methyl 2-pentanone. Okay? All right. So let us continue. And what do I want to do? I want to clear the writing. Can I clear? Nobody's said no. We will head to the right. Look at all the windows I got open. That's exciting. All right. Again, we're being a little mean. Look at this C2H5 here. As soon as you see something that isn't just a methyl group and you're getting close to the end of the chain, right? That's when your brain goes, uh-oh, they're trying to mess with us here. What's our chain here? What's the longest one? What do you got there, Albert? So we got 1. Oops, I need my pen back. Okay, get rid of there. So you're saying then 1, 2, 3, right? 4, 5, and then I got a 6, 7 here. Yeah. So what is this? What's the number goes with it? I'll take the entire thing. Give it to me. 3, 4, 5. oops, extra comma, I got to get rid of that. Trimethyl. Oh, it is a 2. That's okay. 2,4,5 trimethyl -3 heptanone. And I've got some mistakes in there that I'll clean up here. That comma doesn't need to be there. That is a 2. Excellent. 2, 4, 5. My chain heads up that way. Nice job. Okay? Again, you'll notice I'm clock watching. That's all right. I'm as bad as you guys. Except it's opposite. You guys are hoping, gee, I hope he stops talking. And I'm thinking, how much more can I squeeze into this next 10 minutes? Completely different thought processes, but the same actions. Okay. Oh, we're going to draw one, obviously. Let's draw one of these. Okay, so we're going to draw one. Is that true? You guys might have already have it drawn. My little plan of giving you a sheet means that you're waiting for me now. It's totally backwards. I was always waiting for you guys to write the stuff down. Now you're waiting for me. So you've already got this? You've already got it drawn? Okay, well then I'll catch up to you. Here we go. Heptanone. 1, 2, 3, 4, 5. Do you count? Are you laughing that I count it all out? Oh, because I do. I have to count it out. 1, 2, 3, 4, 5, 6, 7. When I get beyond 5, you know it's getting dicey here. So we got a 2 heptanone, double bond O. So that locates my carbonyl group. I got a 3 bromo, Br, a 5 methyl, 4, 5, CH3, and now I'm loading with H's, right? H3, full, right? No H's on that guy. H, H2, H, H2, H3. Did I get it right?
Yeah.
Excellent. You guys, here, I'll do what some of you guys do. I'll give myself a big check. Way to go. All right. It's never good when the students are teaching the teacher. Actually, no, it's great. It means that the student has been elevated. Anyway.
Means you're not on your game.
No, it doesn't.
Yeah. This means we're all right.
I'm sure Yoda is very pleased when the Jedis he teach become great. Of course, they're never as great as Yoda, right? Like, come on, it's Yoda. You see him wield a lightsaber when he fights. Who did he fight? Dooku. That's a classic fight right there. But then he does give up on the Emperor. You're right. Thank you for pointing that out. Actually, it wasn't losing. It was a calculated retreat until Luke could be trained, right? Anyway, let's not be distracted. Let's focus. Aldehyde, yeah, see, look at what you did. Aldehydes and ketones are structural isomers, which means, right, they have the exact same carbons, hydrogens, oxygens. Again, it's just the difference in the position of the double bond. And I think my next slide then is on preparation, and I'm not going to go into the reactions because it does take a while to do a proper explanation of this. So let me just do a little jump ahead on my slide here and take a look, see what it is next. Oh, there are some questions that deal with it. Excellent, perfect, and that's a good place to end. And then tomorrow we'll talk about preparation of these things, both aldehydes and ketones. Some people are downloading the notes and are just filling them in. If you want to do that, this is the type of thing that it probably isn't a bad idea, right? Because it's not like we are writing a lot, but the information is really just little tiny bits of it. If you want to do that, that's always an option. I've always been a writer as well. I always found if I didn't write it, I didn't have that process of making my brain think about it. Yeah. You want me to be louder? I can be louder. Okay, so that's a good place to end for today.